Hi, and welcome to this talk where we'll look into how to use Simplygon to optimize vehicles. My name is Samuel Rantaskola. I've been working with Simplygon for quite some time, about 8 years now. Before that, I was a game developer at a Swedish company called Starbreeze, and at the bottom line, you can see a bunch of the titles that I've been helping out in the development of. The agenda for the talk today is these 3 items. We're first going to start looking at a video that's fresh off the presses, which we call the race. After that, we're going to head into the garage and look at how we used Simplygon to produce the assets we saw in that video. And then finally, we're going to go to the showroom to just quickly look through and scrutinize these objects a bit more. So let's just get into it. Let's start with the race.
Simplygon is for developers who want to accelerate their workflows and maximize the performance of games. Vehicles, for example, are some of the most intensive hard surface objects. Our powerful tools deliver rapid polygon reduction whilst maintaining the exact level of detail you need to race ahead. Vehicles are complex assets, but Simplygon's SDK provides you with tools to tune car LODs to your exact requirements. Simplygon Geometry Datacasters preserve material information which allows you to, for example, change the color on a proxy, supporting customization under demanding optimization specifications. Meshes can be reduced while maintaining hard edges to preserve the shine so your work looks at its best even at the lowest LOD levels. Use Simplygon to create heavily optimized clusters of meshes for distant viewing, ideal for urban environments like cities or any large-scale landscapes. Our processors and tools help you reduce meshes easily and efficiently. Join developers of leading games around the world who solve performance problems and optimize their cars and environments at top speed with Simplygon.
So that was the race. And those vehicles that were displayed in that video, we're now gonna take a closer look at how we did that. And that is gonna be done in the garage. Well, first, a little bit of a disclaimer. While the process described in this video or in this presentation is exclusively done in Unreal Engine, it can be done in any engine or tool using the Simplygon SDK. Basically, all the features we're showing here is available in Max, Maya, or just through the API if you like. We're going to look into this. There are 2 different approaches. The first approach is a straightforward LOD chain. That one is basically just a standard reduction all the way. The second one, which is a little more interesting, is the customizable LOD chain, where we're actually going to look at how you can produce modifiable proxies using Simplygon's remesher and the geometry datacasters. But let's start by looking at what we did before. So the asset we used in this video is actually off the shelf. So we basically kind of had to do some work here to get it to be as we wanted it. So we've started by clustering it. In our case, we chose to cluster it so that, for example, the wheels are separate objects, the doors are separate objects. That way we can then open the doors. The wheels can be animated even at the lowest levels. And finally, we also separated all the transparent parts into one object so that they're not baked into the remesher, which would mean that you would have to have an opacity channel for the whole object, which is not ideal always. Now that we've done the groundwork, let's take a look at how we produce these LOD chains. So the straightforward LOD chain, well, that's pretty straightforward. Well, wow. The first thing you want to do is create LOD recipes. And that you can do in Unreal by just using LOD recipe method. This is basically just settings. In our example here, we used 2 reductions and then we did 3 remeshings to create proxies. If we look a little more in depth here to see what the reduction settings are, we're actually using something called max deviation. Most people that would use Simplegon would probably start with triangle ratio because that's how you've done it in the past. Max deviation is way better because it gives you more control, but I'll go in more detail what that means. So what does max deviation mean? Well, here's an example of a triangle or actually a surface where you have a vertex that is first in the middle vertex here is now going to be reduced down to the plane in the middle or the lower plane. So if we do that, what happens here is basically how much a vertex is deviating from the original position. And that's basically what we're deciding with max deviation. So in our example, the first one used 0.2, which was the unit is centimeters in that example, which means that it's allowed to deviate 2 millimeters. The reason why this way of using it is way more, way better than using triangle percentages is because that allows Simplegon to optimize the object, well, the most efficient way. Some objects tolerate optimization more, for example, a sphere compared to a cube. So with these kind of settings, it gives you more control over the optimization method. However, you're going to have less less exact control over the number of polygons that the resulting object will have. So now that we have set up our settings that we're going to use, we're now just going to go through all the different assets and process them. So basically each of the clusters. And once that's done, we can now assemble the LOD chain. And let's just have a look at that. So here we can see the resulting LOD chain for that object. And that is the straightforward LOD chain. Let's now dig a little bit deeper into the customizable LOD chain. So the customizable LOD chain allows you to change settings on the object after it has been baked into a single proxy. But as the previous one, we're going to start by creating a LOD recipe. And let's have a look at what we do there. So in Unreal, you can do this using our LOD recipe method, but it's basically a set of settings in Simplegon. When we do remeshing, we're using on-screen size. It basically means that we're setting up creating an optimization for a certain screen size. The other thing we're going to do here is we're going to add 2 geometry data casters. And these are basically transferring or material information or geometry information from the original to the optimized object. The first one is texture coordinates. So basically we're creating a texture that contains the original texture coordinates. And the second one is material IDs, which basically is a texture where all the material IDs map from basically original to the optimized version, where a link so that you know which material was used in the original at a certain area of the car. Now that we've set that up, we can process the asset. And let's take a look at what the resulting textures are. So here is the text chord texture. Basically, this is, we're only using the red and the green channel, because this is, the red basically translates to the U and the green translates to the V part of the UVs of the original. So this way we can then map which UV coordinate in the original texture, so that we can look that up. The other part is the material IDs. And material IDs is, I mean, it looks black, but it's because there's only 6 materials in this. If we amp up the contrast here a bit, we will see that there's actually a set of different materials. So each of these nuances of red is a link to another material. So when you're looking up a pixel in the optimized version, you can then find out what was the material ID in the original version. And with these two textures, we can set up a shader. Now, as I said, this was a generic asset, which was not built for this specific case, which means that we have to do a little more intricate shader in order to be able to modify the color, which is what we chose to do in our example. So what you have here is that you first have a color coming in and a material ID. Basically, I want to transfer this, colorize this material ID to this color. Then when you're you're basically shading a pixel, you're looking up if that pixel has that material ID. Then you move on and check, so what was the original texture coordinates for this pixel? And the reason you need to do that is because since this was not custom built for or built for this purpose, we had to add a mask texture so that we know which parts of the original object should be tinted, basically. As you can see here, the mask texture has a bunch of Simplygon logos that we didn't want to change the color for. And after you have that, you then take the base color of the optimized object texture and just modify that to the color that's coming in. And basically that's it. The thing is, this is a quite complex shader, and you probably don't want to run it in do it in runtime. So probably when the player, for example, customizes his car and chooses the color, you would then generate the tinted base color and then use that in a lot simpler shader in the runtime, or when the game is actually running. But there is a simpler shader that you can do with this. And that is if you're building the asset with this in mind. In that case, you don't need the texture coordinates because you wouldn't want to create something that you need to mask. That would create additional texture lookups, which is expensive if you want to run it in the game mode. So if you build the asset with this in mind, you could build a shader like this. Basically, you're taking the color and the matte ID in, looking it up for each pixel, like, should I color this? Should I color this texture or this pixel? And then you have a desaturated base color so that you can easily just modify the color and generate a colorized base color for that object, or just calculate the pixel on the fly. It would be significantly cheaper this way to do it. And then finally, when we have this, we can now try out our shader. So here's an example of that shader running in Unreal, where we can modify the different parts using these textures that we just generated. Now, this is a very quick talk, so we're unfortunately, I mean, this is a complex process. There's a lot of details that I'm leaving out here, but there is actually a blog on our webpage where if you scan this QR code, you'll get transferred to that, where this process is showed, and in this case, it's actually shown in Unity. It's where we're basically processing a share and allowing you to change the materials for the different parts. So if you want to dig deeper into this, have a look at that blog or just reach out to us and we can explain it more in detail. And finally, we now have the shader, we have the object, we can now assemble the LOD chain and try it out. And here it is. Let's just change the color and step through the LOD chain. And there you go. That's your customizable car with super optimized last LODs. So as I said, super optimized. Well, let's have a look what actually this car is. Well, let's scrutinize it a little bit more. So here is the showroom. Let's take a look at this and just circle around a bit. First, let's look at how optimized this car actually is. Let's look in wireframe and just zoom around a bit here and see what happens. As you can see, the first three, like LOD1 and LOD2, is just reductions, and then we're going into the remeshings. But we need to scrutinize this a bit closer, so let's have a look from the side here. Stepping through these, you can see that there are, of course, differences, but we are now looking at this very close up. What happens if we look at it at a bit more reasonable distance? Well, you can see that there's barely any difference. But let's select another color for the car. And just step through the LOD chain once again. And as you can see, not too many difference. And we can also look at this car. Like this car is operatable. You can spin the wheels, toggle the doors, and all that. But we can also scrutinize all the details in more detail. So here for the reduced components, they're all kept separate. So let's look at this door and see how that is optimized. As we step through here, you'll see that it retains the shininess and it doesn't change much as you toggle through. Let's look at the steering wheel here and see in wireframe. This is the LOD3. Let's go back to LOD0 and step through, and you can see that it's heavily optimized as we switch through here. And the same thing, just look at a wheel using the same method here, just stepping through, seeing that we're taking away a lot of polys for each of these steps. And that basically concludes our demonstration. Very quick talk on a complex topic. Feel free to reach out to us. If you want to learn more about this, we could drill into this showroom a bit more. Just mail us at, well, you'll find us at simplegon.com and reach out to us if you want to talk. You have a great day and thank you for listening to this talk.